Smart Hybrid Energy Networks. Part 1. Introduction to Smart Hybrid Energy Networks. In an era defined by technological innovation and climate consciousness, energy systems are undergoing a transformative shift. Gone are the days when centralized power plants supplied electricity to passive consumers over vast grids. Today, energy is becoming smarter, cleaner, and more dynamic. At the heart of this transformation lies the concept of Smart Hybrid Energy Networks, SHEN. Smart Hybrid Energy Networks represent the convergence of various energy sources, renewable and conventional, into a unified, intelligent, and adaptable system. They combine the strengths of diverse energy types, such as solar, wind, hydro, biomass, and even traditional fossil fuels, managed through smart technologies and driven by data. But what makes SHEN so revolutionary? At their core, these networks are smart. They use real-time data and intelligent algorithms to optimize energy flow, demand, and storage. They are hybrid, combining multiple energy sources and storage systems to improve resilience and reduce dependence on any single source. And they are networks, interconnected systems that promote decentralization, collaboration, and bi-directional energy flow. This course serves as your guide to understanding the rise of SHEN, their technical underpinnings, practical applications, and role in building a sustainable energy future. Part 2. The Global Energy Landscape. To appreciate the value of SHEN, we must first understand the energy landscape today. The 21st century faces a dual energy challenge, meeting the growing energy demands of a rising global population while reducing carbon emissions to combat climate change. As developing nations industrialize and urbanize, energy consumption is skyrocketing. Meanwhile, the climate crisis demands a swift departure from fossil fuel dependency. This tension has spurred interest in renewable energy. Over the last decade, the cost of solar panels and wind turbines has plummeted, making renewables more accessible than ever. Yet despite this progress, renewables still struggle with reliability due to their intermittent nature. The sun doesn't always shine, and the wind doesn't always blow. This is where hybrid systems come in. By integrating multiple sources, including traditional ones, and adding storage, we can maintain a steady and resilient power supply. Part 3. Why we need smart hybrid systems. Traditional energy systems are linear. Energy is produced at large-scale plants and transmitted through a one-way grid to consumers. This model is rigid and prone to failure, especially under stress from high demand, natural disasters, or cyber attacks. Smart hybrid energy networks offer a solution. By distributing generation across multiple smaller sources, like rooftop solar panels, wind farms, and biomass plants, and using smart sensors and automation to manage them, SHEN enables a resilient, adaptable, and efficient energy system. The benefits are multifaceted. Decarbonization. By combining renewables with storage and efficient management, SHEN drastically reduces carbon emissions. Decentralization. Localized production reduces transmission losses and empowers communities. Flexibility. Hybrid systems can adapt to changing loads and supply conditions in real time. Resilience. If one part of the system fails, others can compensate, avoiding blackouts. Economic efficiency. Intelligent energy use minimizes waste and reduces costs over time. Part 4. Components of Smart Hybrid Energy Networks. Smart Hybrid Energy Networks, SHEN, are not built from a single technology or energy source. Instead, they are an ecosystem of interdependent components, each playing a crucial role in delivering reliable, sustainable, and efficient energy. In this part, we break down the major components that make up SHEN and explore how they function together to create an intelligent and resilient energy infrastructure. Energy generation sources. SHEN draws power from a diverse mix of generation sources, often categorized into two types: renewable and conventional. A. Renewable energy sources. Solar photovoltaic, PV, converts sunlight directly into electricity using semiconductor materials. Widely adopted for both grid-scale and rooftop installations. Wind turbines harness kinetic energy from wind and convert it to electricity. Offshore and onshore wind farms are key players in hybrid systems. Hydropower uses flowing water to generate electricity. Small-scale hydropower is especially useful in SHEN for regional systems. Biomass and biogas, organic materials, like agricultural waste, can be converted into usable energy through combustion or anaerobic digestion. Geothermal extracts heat from the Earth's core, useful in regions with accessible geothermal reservoirs. Conventional sources. Natural gas, often used as a backup or peaking power source due to its ability to quickly respond to demand. Diesel generators, though not sustainable, they can play a temporary role in remote or off-grid hybrid setups. The power of SHEN lies in its ability to intelligently switch between or combine these sources to ensure a stable supply. 2. Energy storage systems. Storage is the backbone of a flexible and reliable SHEN. It compensates for the intermittent nature of renewables and balances supply with demand. Types of storage. Battery energy storage systems, BESS. Lithium-ion batteries are the most common. They store excess power when production is high and release it when needed. Pumped hydro storage. Water is pumped to a higher elevation during excess generation and released through turbines when energy is needed. Thermal storage stores heat energy for later use in heating systems or conversion to electricity. Hydrogen storage. Excess electricity is used to produce hydrogen through electrolysis. The hydrogen can then be stored and later used in fuel cells. A well-designed SHEN uses predictive algorithms to determine when to charge or discharge storage systems for maximum efficiency. 3. Power electronics and converters. To integrate various energy sources and storage systems, SHEN requires advanced power electronics. These devices manage the conversion, conditioning, and distribution of energy across the network. Key devices include inverters convert DC from solar panels or batteries to AC, which is used by most appliances and the grid. Converters handle DC-DC or AC-AC voltage conversions for compatibility between components. Smart meters measure and communicate real-time data on energy consumption, generation, and grid interaction. Controllers govern the interaction between components, applying optimization algorithms for load balancing and stability. 4. Communication and control infrastructure. The smart in SHEN comes from its digital intelligence, enabled by sensors, communication networks, and control algorithms. Core elements. Supervisory control and data acquisition, SCADA, centralized system that monitors, collects, and controls energy flows in real time. Internet of Things, IoT devices, sensors and actuators gather data from across the network, enabling automation and remote control. Communication protocols enable data exchange between devices, often using Wi-Fi, 5G, Zigbee, or proprietary protocols for reliability. Edge and cloud computing processes vast amounts of data to run AI models, forecast demand, optimize resources, and prevent faults. This infrastructure ensures that SHEN remains self-regulating, adaptive, and transparent. 5. Distribution and microgrid systems. Distribution systems connect generation and storage with consumers, often via microgrids, localized grids that can operate independently or with the main grid. Features of microgrids. Islanding capability can disconnect from the main grid during outages and continue operating. Peer-to-peer energy trading. Consumers can generate, store, and sell energy to neighbors via blockchain or smart contracts. Resilient architecture. Decentralized layout improves system reliability and limits the impact of failures. SHEN can consist of multiple microgrids linked into a macro network, forming an energy web rather than a centralized grid. 6. Consumers and prosumers. In SHEN, consumers are no longer passive. Many become prosumers, both producing and consuming energy. Roles of prosumers. Feed-in tariffs or net metering. Sell surplus energy back to the grid. Demand response participants. Adjust consumption in response to grid signals, e.g., using appliances during off-peak hours. Energy storage owners. Store electricity and use it during peak pricing or outages. By engaging end users in energy management, SHEN promotes sustainability and grid participation. 7. Regulatory and financial frameworks. Though not a physical component, policy and finance are vital enablers. Governments and institutions must provide incentives for hybrid systems, e.g., tax credits, subsidies. Clear interconnection standards for distributed energy resources, DERs. Dynamic pricing models that reflect real-time grid conditions. Financing mechanisms for infrastructure investment and innovation. Without the right regulatory ecosystem, even the most advanced SHEN technologies can stall in deployment. Conclusion. Smart hybrid energy networks are composed of diverse, interconnected technologies, each crucial to the system's performance. Generation, storage, control, and end-user participation all come together in a harmonized structure managed through digital intelligence. As we progress to more complex parts, we will explore how these components interact in real-world settings, how they are managed, and what challenges arise in building and operating such systems. Part 5. Smart Grids and IoT Integration. The transformation from traditional energy systems to smart hybrid energy networks, SHEN, is not just about replacing fossil fuels with renewables. It's about making the grid intelligent, responsive, and self-regulating. At the heart of this transformation lies the smart grid, supercharged by the Internet of Things, IoT. In this part, we'll explore how smart grids work, how IoT devices enable real-time control and optimization, and why their integration is critical for the success of hybrid energy systems. What is a smart grid? A smart grid is an energy infrastructure that uses digital communication technologies, automated control systems, and advanced analytics to manage the generation, transmission, distribution, and consumption of electricity in real time. Key features: two-way communication between utilities and consumers, self-healing capabilities during faults or outages, demand-side management and load balancing, dynamic pricing based on real-time data, integration of distributed energy resources, DERs. Where traditional grids are static and centralized, smart grids are adaptive, interactive, and data-driven. 2. The role of IoT in SHEN. The Internet of Things, IoT, refers to a network of physical devices, sensors, meters, controllers, that are embedded with software and connectivity to collect and exchange data. In SHEN, IoT acts as the nervous system, continuously sensing, transmitting, and acting upon real-world conditions. Common IoT devices in SHEN. Smart meters track energy usage in real time and communicate with both the consumer and utility. Grid sensors monitor voltage, current, frequency, and temperature across the network. Smart appliances adjust operations based on grid signals to save energy and reduce peak demand. EV chargers optimize charging schedules based on grid load and renewable availability. Weather stations predict solar and wind input for renewable forecasting. By equipping each component of SHEN with sensors and connectivity, the entire network becomes responsive and self-aware. 3. Communication technologies. To function effectively, smart grids and IoT devices need reliable high-speed communication. Several technologies are used, depending on application and location. Communication protocols and networks. Wi-Fi and Zigbee, common in home energy management systems. LoRaWAN, long-range low-power option for remote areas. 5G, high bandwidth and ultra-low latency, ideal for real-time control. Powerline communication, PLC, sends data over existing electrical lines. Fiber optics, high-capacity backbone for grid data transmission. A well-designed SHEN typically uses a hybrid communication infrastructure to balance cost, speed, and reliability. 4. Data collection and analytics. Data is the fuel of a smart grid. IoT devices continuously generate vast volumes of data, known as big energy data. But raw data alone is not useful. It must be processed into actionable insights. Analytics in SHEN. Load forecasting predicts energy demand at different times and locations. Renewable forecasting anticipates solar wind output using weather models. Fault detection and localization identifies failures before they cause blackouts. Asset management tracks equipment health and schedules predictive maintenance. Energy theft detection recognizes unusual consumption patterns or tampering. Modern SHEN platforms use AI and machine learning to enhance decision-making, automate responses, and continuously optimize performance. 5. Grid automation and control systems. Smart grids rely on automation to respond in real time to changing conditions. This is achieved through layered control systems. Hierarchy of grid control. Primary control device level, fast local responses, e.g. voltage regulation. Secondary control, substation level, balances loads and frequency across local grids. Tertiary control, network level, manages power exchange between microgrids or with the main grid. Energy management systems, EMS, centralized intelligence for optimal energy scheduling and dispatch. Grid automation ensures stability, reliability, and efficiency, especially during peak demand, renewable fluctuations, or emergencies. 6. Demand response and smart consumption. One of the game-changing aspects of smart grids is demand response, DR, the ability to adjust electricity usage in response to grid conditions or pricing. How demand response works. When demand is high or supply is low, the grid sends signals to reduce load. Smart thermostats, water heaters, or industrial machines can adjust their usage automatically. Users are incentivized through lower tariffs or credits to participate. This dynamic balancing of supply and demand is vital for hybrid systems where renewable output can be unpredictable. 7. Challenges in smart grid and IoT integration. Despite the advantages, building a digital energy infrastructure comes with challenges. Interoperability. Devices from different manufacturers must work together. Data privacy. Protecting consumer energy data from misuse. Cybersecurity. Preventing hacking of critical grid infrastructure. Latency and bandwidth. Ensuring real-time communication under load. Cost of deployment. Upfront investment in devices, networks, and training. Solving these challenges requires a combination of standardization, innovation, and regulatory support. 8. Real-world applications. Europe's smart grid evolution. Countries like Germany and Denmark have integrated smart grids with high levels of wind and solar using IoT-based controls. India's smart meter rollout, aiming for millions of smart meters to improve grid reliability and reduce losses. U.S. demand response programs. Utilities like PG&E and Con Edison use smart grid tech to manage demand during heat waves and emergencies. These case studies show how SHEN can scale across diverse economic and geographic contexts with smart grid integration. Conclusion. Smart grids and IoT are the digital backbone of smart hybrid energy networks. They transform the energy system from a rigid one-way flow into a flexible data-driven web capable of self-optimization. As we move forward, these technologies will play an ever-growing role in managing complexity, reducing emissions, and empowering both consumers and prosumers in the energy transition. Part 6. Renewable energy sources. Renewable energy is the foundation of any smart hybrid energy network, SHEN. These clean, sustainable sources provide the core power that fuels the shift away from fossil fuels. However, their integration requires strategic planning and technological support due to their variability and geographic dependency. In this part, we'll explore the major types of renewable energy, their roles in hybrid networks, and how SHEN technologies help overcome their limitations. Why renewables matter. The urgency of climate change has accelerated the global transition to renewable energy. Unlike fossil fuels, renewables produce little to no greenhouse gas emissions and are derived from sources that are naturally replenished. Key benefits of renewables. Environmental sustainability, drastically lower carbon emissions and pollution. Energy independence, reduces reliance on imported fuels. Cost competitiveness, plummeting prices of solar and wind make them viable. Decentralized access, ideal for off-grid and rural applications. In SHEN, renewables provide the primary energy input, often supported by storage and smart control systems to ensure reliability. 2. Solar energy. Solar power is the most widespread and rapidly growing renewable source in SHEN. Types of solar technologies. Photovoltaic, PV panels, convert sunlight directly into electricity using semiconductor materials. Common in residential and utility-scale installations. Concentrated solar power, CSP, uses mirrors or lenses to focus sunlight and produce heat, which drives a steam turbine. Advantages. Modular and scalable, rooftop to megawatt scale. Silent, low-maintenance operation. Suitable for most geographic locations. Challenges. Intermittent, only available during daylight. Requires storage or grid support for continuous power. SHEN addresses these challenges by pairing solar with battery storage, AI forecasting, and load shifting. 3. Wind energy. Wind power is another major pillar of renewable generation in hybrid systems. Types of wind installations. Onshore wind farms, built on land typically in open plains or hilltops. Offshore wind farms, installed in bodies of water where winds are stronger and more consistent. Advantages. High energy output in suitable areas. Fast construction and scalability. Complements solar well, often windy at night. Challenges. Variable and site-specific. Visual and acoustic impact in some communities. Requires grid balancing. SHEN incorporates wind energy into a dynamic mix, using predictive algorithms and hybridization to ensure smooth integration with other sources. 4. Hydropower. Hydropower is the most mature renewable energy technology, converting flowing water into electricity. Types of hydropower. Large-scale dams provide baseload power and grid stability. Small hydro, microhydro, ideal for rural and off-grid applications. Run-of-river systems generate power without large reservoirs, minimizing environmental disruption. Advantages. Highly reliable and controllable. Can provide energy storage via pumped hydro. Long lifespan with low operating costs. Challenges. High upfront costs. Environmental and ecological concerns. Limited to regions with suitable water flow. In SHEN, small hydro often plays a stabilizing role, complementing intermittent renewables. 5. Biomass and biogas. Biomass uses organic materials like wood chips, agricultural waste, or even algae to produce energy through combustion or gasification. Biogas, produced via anaerobic digestion of organic waste, can be used for heating or electricity. Applications. Rural and agricultural communities. Waste-to-energy systems. Combined heat and power, CHP plants. Advantages. Utilizes waste materials. Provides dispatchable power, controllable generation. Supports circular economy and waste management. Challenges. Requires careful fuel sourcing and sustainability. Emits some pollutants. Not always carbon neutral if deforestation occurs. SHEN can incorporate biomass as a backup source for renewable heavy networks or in hybrid microgrids for rural electrification. 6. Geothermal energy. Geothermal taps into the Earth's internal heat to generate electricity or provide direct heating. It's highly site-specific but offers constant base load power. Advantages: stable and reliable, 24/7 operation. Small land footprint. Minimal emissions. Challenges: high drilling costs and exploration risks. Limited to geothermal-rich regions. Requires careful resource management to avoid depletion. When available, geothermal is an excellent addition to SHEN due to its predictability and high capacity factor. 7. Hybridization of renewables. One of the strengths of SHEN is the ability to combine different renewable sources to balance their strengths and weaknesses. Common hybrid setups. Solar plus wind plus battery, most common hybrid combo. Wind can produce power at night, balancing solar's daytime generation. Solar plus hydro. Hydro ramps up when solar drops, especially during cloudy or evening hours. Biomass plus solar. Biomass provides steady backup when solar is unavailable. SHEN uses smart controllers and energy management systems to coordinate these resources, ensuring consistent and cost-effective energy delivery. 8. Forecasting and integration technologies. Integrating renewables requires accurate generation forecasting and grid synchronization. Key tools: weather forecasting APIs integrated into EMS. Machine learning algorithms for solar and wind prediction. Grid forming inverters to stabilize frequency and voltage. Virtual power plants, VPPs, that aggregate small renewable producers. These technologies help SHEN mitigate intermittency, increase reliability, and support greater renewable penetration. Conclusion: renewable energy sources are the lifeblood of smart hybrid energy networks. While each source has its unique challenges, SHEN leverages smart technologies, hybrid strategies, and energy storage to create a resilient, low-carbon energy system. As renewable adoption continues to grow, the role of SHEN in coordinating and maximizing their potential will only become more critical. Part 7. Energy Storage Technologies. One of the greatest challenges in modern energy systems is the mismatch between when energy is produced and when it is needed. Renewable sources like solar and wind are intermittent and variable by nature. Without energy storage, a hybrid network would struggle to maintain stability, reliability, and efficiency. That's where energy storage technologies (ESTs) come in. In this part, we'll explore the various types of storage technologies used in smart hybrid energy networks, SHEN, their functions, use cases, and how they enable energy independence and grid stability. Why energy storage is essential. Storage gives SHEN the flexibility to store excess renewable energy for use during low generation periods, smooth out fluctuations in supply and demand, provide backup power during outages, optimize energy usage based on real-time pricing, enable off-grid operation and microgrid autonomy. Think of energy storage as the battery pack of the energy internet, capturing data-driven decisions and storing energy when it's most strategic. 2. Battery Energy Storage Systems, BESS. Batteries are the most common and scalable form of energy storage in SHEN. They convert electricity into chemical energy and back, offering rapid response and flexibility. Types of batteries. A. Lithium-ion, Li-ion. Most widely used in residential, commercial, and grid-scale systems. High energy density, efficiency, -90 to 95%, and fast charging. Common in electric vehicles and home energy storage, e.g. Tesla Powerwall. B. Lead-acid. Traditional and cost-effective. Lower energy density and shorter lifespan. Still used in small off-grid setups and backup power systems. C. Flow batteries, e.g. vanadium redox. Energy stored in liquid electrolytes. Excellent for long-duration storage and deep cycling. Scalable for large grid or microgrid applications. D. Sodium-based batteries, e.g. sodium-ion. Emerging tech, offering a cheaper, abundant alternative to Li-ion. Lower energy density, but promising for stationary storage. Advantages of BESS. Fast response times, milliseconds. Modular and scalable. Ideal for frequency regulation, peak shaving and self-consumption. Challenges. Degradation over time. Fire and thermal risks, especially with Li-ion. High upfront costs, though declining. 3. Mechanical storage systems. These systems store energy as potential or kinetic energy, typically for grid-scale applications. A. Pumped hydro storage. Water is pumped uphill using excess electricity, then released through turbines to generate power. Most widely deployed form of grid-scale storage worldwide. Pros. Long lifespan, 50+ years. Huge capacity and efficiency, -80%. Cons. Requires specific topography. High capital costs and environmental impact. B. Compressed air energy storage, CAES. Air is compressed and stored in underground caverns, then released to drive turbines. Used for bulk energy storage and grid balancing. C. Flywheels. Store energy as kinetic energy in a spinning rotor. Deliver high power quickly and recharge rapidly. Best for short-duration high-frequency applications, like voltage support. 4. Thermal energy storage. This type stores energy in the form of heat or cold, often used in heating, cooling, or industrial processes. Examples. Molten salt storage, used in concentrated solar power, CSP, plants to store heat for nighttime electricity generation. Ice storage systems, store ice at night to reduce HVAC demand during the day. Phase change materials, PCM, store and release energy during phase transitions, e.g. solid to liquid. Use cases in SHEN. District heating and cooling networks. Renewable industrial heat systems. Load shifting for commercial buildings. 5. Hydrogen and power-to-X technologies. Excess electricity can be used to produce hydrogen through electrolysis, which can then be stored, transported, or converted back to electricity using fuel cells. Hydrogen storage applications. Seasonal energy storage, store summer solar for winter use. Fuel for fuel cell vehicles or industrial processes. Power to gas, injecting hydrogen into natural gas pipelines. Advantages. Long duration and seasonal storage. Versatile end uses, electricity, fuel, heat. Challenges. Low round-trip efficiency, 30 to 40%. High costs and infrastructure needs. Safety concerns with handling hydrogen. Hydrogen is especially useful in SHEN for long-term decarbonization and multi-sector integration. Electricity plus transport plus industry. 6. Energy storage use cases in SHEN. Storage supports SHEN across all levels. A. Residential. Maximize self-consumption of rooftop solar. Reduce electricity bills by storing energy during off-peak pricing. Backup during grid outages. B. Commercial and industrial. Demand charge reduction. Grid participation through frequency regulation or demand response. Increased energy resilience. C. Utility and grid level. Load leveling and time shifting of renewable energy. Black start capability, restoring power without grid assistance. Integration of high renewable penetration. 7. Energy management systems, EMS, and optimization. Storage systems in SHEN are not standalone. They're coordinated through intelligent energy management systems, EMS, that monitor grid conditions and forecast demand, optimize when to charge or discharge, balance multiple storage technologies, enable stacking of revenue streams, e.g., peak shaving plus grid services. With AI and machine learning, EMS can improve over time, increasing system efficiency and reliability. 8. Economic and environmental considerations. While storage brings numerous benefits, it's important to evaluate economic factors. Levelized cost of storage, LCOS, payback period, and return on investment. Incentives and subsidies for battery installation. Environmental factors. Mining impacts, especially for lithium and cobalt. Battery recycling and disposal. Land use, especially for pumped hydro or hydrogen. Sustainable SHEN designs must consider both cost and environmental lifecycle impacts. Conclusion. Energy storage is the cornerstone of smart hybrid energy networks, enabling them to function reliably and efficiently despite the intermittency of renewable sources. Whether through batteries, pumped hydro, thermal systems, or hydrogen, storage empowers SHEN to deliver on its promise of clean, resilient, and smart energy. As storage technologies advance and costs decline, their role in the energy landscape will only grow. Part 8. Microgrids and Decentralized Energy Systems. The global energy landscape is undergoing a shift, from centralized top-down grids to localized, decentralized, and intelligent energy systems. At the forefront of this evolution are microgrids and decentralized energy systems, both core components of smart hybrid energy networks, SHEN. They offer increased energy autonomy, resilience, and sustainability, especially in remote areas, disaster-prone zones, and smart cities. This part explores what microgrids are, how they operate within SHEN, and why decentralization is a game-changer in the energy transition. What is a microgrid? A microgrid is a localized energy system that can operate independently or in coordination with the main grid. It consists of interconnected loads, distributed energy resources, DERs, storage and control systems. Key characteristics. Island mode can disconnect from the main grid and operate autonomously during outages or emergencies. Grid-connected mode exchanges energy with the larger grid when available or beneficial. Smart control, real-time monitoring, energy optimization, and fault detection. In SHEN, microgrids serve as modular building blocks capable of powering communities, campuses, military bases, and industrial parks with hybrid energy sources. 2. Components of a microgrid. A well-functioning microgrid integrates multiple technologies working seamlessly together. A. Distributed energy resources, DERs. Solar PV systems. Wind turbines. Biomass, biogas generators. Small hydro units. B. Energy storage. Batteries, Li-ion flow, etc. Thermal storage. Flywheels or other mechanical storage. C. Loads. Residential, commercial, or industrial energy consumers. Smart appliances and EV charging stations. D. Control and communication systems. Microgrid controller or EMS energy management system. IoT-enabled sensors and meters. Data analytics and AI optimization algorithms. E. Backup systems. Diesel or gas generators as last resort backup supply. Hydrogen fuel cells or CHP units. 3. Decentralized energy systems, DES. Decentralization refers to the generation and management of electricity at or near the point of consumption, minimizing transmission losses and enabling consumer participation in energy production. Core principles of DES. Prosumers, users who both produce and consume energy, e.g., homes with rooftop solar. Peer-to-peer trading, local energy exchange through digital platforms or blockchain. Community ownership, co-op or municipally owned energy systems. Energy democracy, greater control and transparency for local stakeholders. SHEN leverages DE to empower users, reduce reliance on centralized utilities, and create energy equity. 4. Benefits of microgrids and DE in SHEN. Energy resilience. Microgrids continue operating during outages or disasters, providing life-saving power. Efficiency and loss reduction. Local generation reduces transmission and distribution losses. Scalability and modularity. Microgrids can scale up by connecting additional units or remain small for specific applications. Renewable integration. Easier to match renewable generation with local demand and storage. Tailored solutions. Each microgrid can be designed based on local resources, needs, and socioeconomic factors. 5. Types of microgrids. A. Remote microgrids off-grid. Completely disconnected from the national grid. Used in rural electrification, islands, mining operations, and remote research stations. B. Grid-tied microgrids. Normally connected to the grid, but can switch to island mode when needed. Common in urban campuses, industrial zones, and smart communities. C. Virtual microgrids. A coordinated cluster of DERs and loads across different locations, connected digitally. Enabled by IoT, cloud computing, and blockchain. 6. Microgrid control strategies. Control systems are the brain of a microgrid, ensuring stability, optimization, and coordination of resources. Control hierarchy. Primary control manages voltage and frequency in real time. Secondary control maintains power quality and load balancing. Tertiary control optimizes cost, energy flow, and interactions with external grids or markets. Technologies used. Predictive AI for demand forecasting. Smart inverters and relays for dynamic switching. Blockchain for secure transactions and peer-to-peer energy trading. 7. Use cases around the world. A. India, solar microgrids for rural villages. Thousands of small microgrids are providing electricity to villages previously in the dark, often operated by local cooperatives or startups. B. California, campus microgrids. Universities like UC San Diego operate smart microgrids to reduce emissions, cut costs, and maintain reliability. C. Sub-Saharan Africa, decentralized mini-grids. Donor-funded and private sector projects using SHEN principles to electrify remote communities. D. Japan, disaster-resilient grids. Post-Fukushima, many towns have invested in microgrids with renewable and storage systems to ensure local energy security. 8. Integration with the main grid and SHEN. In a fully developed SHEN, microgrids are nodes within a larger smart energy web, interacting fluidly with the national grid for energy exchange and backup. Other microgrids through virtual or physical connections. Smart buildings and cities that optimize energy use in real time. Markets via demand response and distributed energy trading. This decentralized yet connected approach enhances flexibility, reliability, and sustainability across the energy system. 9. Challenges and future opportunities. Challenges. Complex coordination and control. Regulatory and interconnection barriers. High initial costs for setup and automation. Cybersecurity risks with IoT integration. Opportunities. AI-driven microgrid controllers. Blockchain-enabled energy markets. Microgrid as a service business models. Integration with electric vehicles and smart homes. The shift toward decentralized energy is not only about tech, it's about reshaping how we think about ownership, participation, and power itself. Conclusion. Microgrids and decentralized energy systems are essential building blocks of smart hybrid energy networks. They localize energy generation, improve resilience, and empower communities. With continued innovation in control systems, storage, and policy, microgrids will play a central role in the global energy transition, bringing energy where it's needed most, how it's needed most, and by whom it's needed most. Part 9. Electric Vehicles and Grid Interaction. Electric vehicles, EVs, are more than just a clean transportation alternative. They are rapidly becoming mobile energy assets. When integrated into smart hybrid energy networks, EVs can store, supply, and even trade electricity. This part explores the relationship between EVs and the grid, known as vehicle-to-grid (V2G) interaction, and how EVs contribute to the future of decentralized, sustainable energy systems. EVs in the energy ecosystem. Traditionally, transportation and energy systems have been separate. However, electrification of vehicles is blending these sectors, with significant implications for energy demand, grid stability, and emissions. Roles of EVs in SHEN. Flexible loads. EVs can charge when renewable supply is high or electricity prices are low. Mobile storage units store excess energy and feed it back when needed. Grid balancers help stabilize frequency and voltage during demand peaks or generation dips. Distributed energy resources (DERs) act as part of a broader smart grid. 2. Types of EV grid interaction. There are several levels of interaction between EVs and energy systems. A. Unidirectional charging, V1G. EVs draw electricity from the grid to charge. Can be smart charged based on price signals, renewable availability, or grid demand. B. Bidirectional charging, V2G. EVs can return electricity to the grid. Turns EVs into energy storage systems on wheels. Can support peak shaving, frequency regulation, and emergency backup. C. Vehicle-to-home, V2H, and vehicle-to-building, V2B. EVs power homes or buildings during outages or peak pricing. Ideal in areas with unreliable grids or high time of use, TOU rates. D. Vehicle-to-everything, V2X. Umbrella term covering all forms of grid interaction. Includes communication with other vehicles, smart traffic systems, and infrastructure. 3. Smart charging infrastructure. A critical element for integrating EVs into SHEN is the deployment of smart, connected charging stations. Smart charging features. Time of use and dynamic pricing. Renewable-powered charging, e.g. solar carports. Load management to avoid overloading transformers. Integration with home energy management systems, HEMS. Charging types. Level 1, standard household outlet, slow charging. Level 2, faster, requires 240 volts connection, common in homes and workplaces. DC fast charging, very rapid, ideal for public stations and long-distance travel. Wireless charging, emerging tech for seamless cable-free operation. 4. Battery capacity and grid support. EVs typically have large battery capacities, ranging from 30 kilowatt-hours to 100 plus kWh, which can be leveraged to store solar or wind energy during the day. Support the grid during evening peaks. Provide backup during blackouts. Example. A fully charged 60 kilowatt-hour EV can power a typical home for 2 to 3 days. In SHEN, aggregating thousands of EVs creates a virtual power plant, VPP, that can participate in energy markets or support grid stability. 5. V2G in action, real-world pilots. A. Nissan Leaf and V2G in Europe. Trials in the UK, Netherlands, and Denmark have shown EVs reducing energy costs and supporting the grid. Users earn money for providing grid services. B. School buses in California. Electric school buses charge at night and discharge during the day to support the grid when students are in class. C. Japan's emergency energy model. After natural disasters, EVs provided critical power to homes, hospitals, and shelters. These real-world examples show how EVs, when connected to SHEN, can move from consumers to contributors. 6. Challenges of EV grid integration. While promising, EV grid interaction comes with some hurdles. Battery degradation. Frequent charging and discharging may reduce battery lifespan, though managed V2G minimizes this. Standardization. Compatibility issues between vehicles, chargers, and communication protocols. Infrastructure gaps. Insufficient fast charging networks in many regions. Regulatory barriers. Unclear rules for energy buyback, grid participation, and revenue models. 7. EVs in SHEN planning and optimization. In smart hybrid energy networks, EVs are fully integrated into energy planning tools. Demand forecasting, predict when and where EVs will charge. Grid optimization, adjust charging schedules based on renewables or demand. Revenue stacking, monetize V2G participation, frequency regulation, and demand response. Smart routing, use traffic and grid data to optimize where EVs charge. EVs, when connected to AI-based EMS, become smart mobile nodes within a larger intelligent grid. 8. EVs and renewable energy synergy. EVs can act as buffers for renewable energy. Charge midday when solar production peaks. Discharge at night to cover solar deficits. Absorb wind energy during low-demand hours. This synergy smooths out the variability of renewables, helping SHEN maintain balance and efficiency. 9. Future trends and innovations. Solid-state batteries offer higher energy density, faster charging, and longer life. Could accelerate V2G adoption. Blockchain-based EV energy trading. Enable peer-to-peer EV energy swaps and decentralized markets. Optimize charging fleets. Fleet managers use predictive algorithms to minimize cost and grid impact. Mobile microgrids. EVs form pop-up microgrids for events, emergencies, or remote areas. Conclusion. Electric vehicles are no longer just modes of transport. They are key players in the smart energy ecosystem. When integrated into SHEN, EVs provide grid stability, storage capacity, and resilience. With smart charging, V2G, and predictive control, EVs turn from energy users into energy partners. The road ahead is electric, intelligent, and interconnected. Part 10. Smart homes and buildings. Smart homes and buildings are the interface between users and the energy grid. They are no longer passive consumers of electricity. They are becoming active, responsive, and intelligent participants in SHEN. By integrating automation, energy-efficient technologies, and data-driven controls, these structures help manage energy demand, improve comfort, and support sustainability goals. What makes a home or building smart? A smart home or building uses digital technology to monitor, control, and optimize energy use. This includes everything from smart thermostats and connected lighting to energy dashboards and automated appliances. Core characteristics: real-time energy monitoring, automated control of lighting, HVAC and appliances, integration with renewable energy and storage, communication with the grid and other buildings, data analytics and machine learning for optimization. In the SHEN context, smart buildings are key nodes that adjust consumption in response to grid needs, renewable availability, and user preferences. 2. Key technologies in smart buildings. A. Building energy management systems, BEMS. Software and hardware that monitor and control energy use. Can optimize lighting, heating, cooling, ventilation, and power consumption. Integrates with SHEN to respond to grid signals or price changes. B. Smart meters and submeters. Measure real-time electricity, gas and water use. Enable granular control and billing transparency. C. IoT devices and sensors. Motion sensors, occupancy detectors, and ambient light sensors. Trigger automated actions like dimming lights or adjusting temperature. D. Smart appliances. Washing machines, fridges, HVAC units that communicate with energy systems. Can delay operation until energy is cheapest or most abundant. E. Home energy storage. Batteries, e.g., Tesla Powerwall, LG Chem, store solar or off-peak electricity. Support backup power and time of use optimization. F. Energy dashboards and apps. Give users visibility into energy use and trends. Empower behavior change and efficiency. 3. Integration with renewable energy. Smart homes often pair with solar PV systems and storage, making them prosumers within SHEN. Benefits. Self-consumption of solar energy. Reduce dependence on the grid. Backup power during outages. Ability to sell excess energy back to the grid or neighbors. With SHEN, smart homes can participate in peer-to-peer energy trading, becoming mini power plants that feed into a local or virtual energy market. 4. Demand-side management and load flexibility. Smart homes and buildings help SHEN maintain grid balance by adjusting consumption in real time. Examples of load flexibility. Pre-cooling or preheating spaces when electricity is cheap. Delaying EV charging or dishwashing until renewable generation peaks. Participating in demand response programs, earning incentives for reducing load during peak demand. This ability to shift and shape demand transforms users into active grid participants, not just consumers. 5. Smart homes, comfort and health. Beyond energy, smart buildings enhance quality of life. Features. Automated air purification and humidity control. Lighting that mimics natural sunlight. Voice-activated environments, e.g. Alexa, Google Home. Smart security systems and surveillance. With these features, SHEN isn't just about energy efficiency, it's about creating smarter, safer, and healthier living spaces. 6. Smart commercial and industrial buildings. Larger buildings, like offices, malls, and factories, play an even bigger role in SHEN. Advanced features. Integrated HVAC and lighting optimization. Real-time occupancy-based energy control. Building-to-grid B2G participation. Predictive maintenance using IoT sensors. Integration with EV charging stations for employees or fleets. Smart commercial buildings can reduce operational costs while contributing grid services like frequency regulation and voltage support. 7. Interconnection and energy sharing. Through SHEN, buildings can be connected into networks of energy-sharing nodes. Neighborhood-level features. Community battery systems. Shared solar arrays. Dynamic pricing within microgrids. Localized peer-to-peer trading. This enhances energy equity and ensures energy flows where it's most needed in a secure and optimized way. 8. Smart building standards and certifications. There are multiple frameworks for evaluating and certifying smart, sustainable buildings. Popular certifications. LEED, Leadership in Energy and Environmental Design. BREEAM, Building Research Establishment Environmental Assessment Method. WELL Building Standard. Energy Star. Smart Score and Wired Score focus on digital connectivity. These standards help ensure accountability, efficiency, and quality in SHEN-enabled construction and retrofits. 9. Challenges in smart building integration. Despite their benefits, smart buildings face several obstacles. Data privacy. User data collection raises concerns about security and surveillance. Cost and accessibility. High-tech solutions may not be affordable for all households or small businesses. Interoperability. Different devices and systems may not work together seamlessly. Digital literacy. Users need education and support to fully benefit from smart systems. Addressing these challenges is critical to making SHEN inclusive and equitable. 10. Future of smart buildings in SHEN. The next generation of smart homes and buildings will be hyper-connected, seamlessly integrated with the grid, EVs, appliances, and even wearables. AI-driven, using machine learning to personalize and optimize energy use without user input. Sustainable by design. Net zero or net positive energy performance. Use of recycled materials and circular design principles. Community-oriented. Homes that talk to each other, share energy, and respond as a collective in microgrids. These buildings will form the backbone of user-facing SHEN systems. Conclusion. Smart homes and buildings are where the user meets the grid, and the magic of SHEN becomes tangible. Through automation, intelligence, and connectivity, they make energy use more efficient, responsive, and personal. In a SHEN world, our homes and workplaces aren't just spaces, they're partners in a cleaner, smarter, and more resilient energy future.